Did anybody have any questions about alkenes, alkynes, and then I think determining cis-trans and EZ was part of this.
Can you go over the EZ?
The EZ rules? Sure. What other questions did you have?
I have one on like a specific problem, like asking about EZ, and I was just confused as to why one of them wasn't cis-trans. It was 2.34.
34.
Yeah.
This one.
I was wondering, like, is G not like a cis isomer?
No, it's not cis.
Not.
It's definitely not cis. Is it E or Z? We should probably go over that. So let's do this. Let's look at this problem right here as we can kind of review the rules for E and Z. Now, does everybody know when you can use cis and trans and when you can't use cis and trans? No? Okay, then we should probably start all the way at the beginning. So here's the issue. The issue is that when we have a double bond, when we have a carbon-carbon double bond, that means we have four things attached to it. And we have what are called stereoisomers that are possible. So what's a stereoisomer? Well, what's an isomer? An isomer is when you have a molecular formula and you can draw it different ways. So the simplest of isomers is something like I could have ethyl alcohol with a C2H6O, but I could also have dimethyl ether, which is a C2H6O. So I can bond the atoms completely differently. That's one type of isomer. That's called a structural isomer. If I was to have, for instance, a chlorine here, a chlorine here, a hydrogen there, and a hydrogen there, there's actually two possible ways that I could arrange this molecule where it still has the same structure but has different three-dimensional shape. So these two molecules are actually the same structural isomer. And what do I mean by that? Well, what I mean is that if we look at, it's got a carbon-carbon double bond. On this side, this carbon is attached to a chlorine and a hydrogen, and this carbon's attached to a chlorine and a hydrogen. The molecule below is the atoms are attached the same. Carbon with chlorine hydrogen, carbon-carbon double bond, carbon with chlorine and hydrogen. What's different about these is their three-dimensional shapes. Because in this case, the chlorines are kind of opposite each other, and here the chlorines are on the same side of the ring. So that's what the EZ system that's what the EZ system is for, that's what the cis-trans system is for, is to tell us which way the four groups are arranged around the double bond. Now, if you have a hydrogen, if you have one hydrogen and one non-hydrogen group attached to each of the two carbons in the double bond, you can use cis or trans. Because then if I say, well, it's trans, it's pretty clear that I'm talking either about the two hydrogens or the two non-hydrogen groups. So for instance, when either the chlorines or the hydrogens are opposite, that's trans. When the chlorines or the hydrogens are on the same side, that's the cis. So you can only use cis or trans if each of the carbons has one hydrogen and one non-hydrogen group. Because then it doesn't matter, am I talking about the two non-hydrogen groups? Am I talking about the two hydrogen groups? It doesn't matter. It's pretty clear if we say trans, either one of those groups, they're opposite each other. So I'm starting from square one here. Does that make sense to everybody? Like I said, if something doesn't make sense, you got to raise your hand or yell or stop. I don't get it. Then we'll go back. Okay, so that's when we can use cis or trans. Now, where does it break down? It breaks down when, when all of a sudden there's 3 or more non-hydrogen groups on the double bond. Remember, there's a maximum of 4 groups. If 3 or more of those are non-hydrogens, I can't use cis or trans anymore. And I'm going to take a step back here, and I'm going to also say that also remember that if one carbon has the same 2 groups attached to it, that molecule cannot be cis or trans. Because I get the same structure in this case, whether the chlorine is up or down, because the other 2 groups are exactly the same. So this molecule right here is not cis or trans. So when you have one carbon with the same groups on them, there's no cis or trans. And there's also no E or Z. So now all of a sudden we have a molecule over here that has 3 non-hydrogen groups. So now I have to move to the EZ system, which kind of is, but kind of isn't. Easy, right? So first, in order to do EZ, we have to learn what are called the Cahn-Ingold-Prelog sequence rules. Now, this book is throwing naming in the first 3 weeks. Naming everything, right? Which is kind of unique, but we'll survive. Both you and me will survive. It's going to be tough, but we'll survive. And the Cahn-Ingold-Prelog sequence rules are normally done about halfway through the semester when we start talking about R's and S's. But you don't know what R's or S's are, and you don't need to know what they are right at the moment. But think about IUPAC rules. IUPAC rules say that there has to be a system that gives you a unique name. And that system never fails. So what I don't remember what his first name is, it's Sir Kenneth Ingold and Vladimir Prelog, what they had to do was come up with a system that would allow us to tell what the space or what the geometry around the double bond is every time. And the rule can never lead to ties. So we have to break ties constantly. And they looked at the cis-trans system and they said, well, we need something like that. So what I really would like is I would like to look at these 2 molecules or these 2 groups on this carbon, these 2 groups on this carbon, and say one is a high priority group just for these two. I've got one high and one low priority group, and over here I've got one high and one low priority group. And so if we end up with both of the high priority groups on the same side, we're going to name it something other than cis or trans. And if we end up with the high priority groups opposite each other, we're going to come up with another term for it, not cis or trans, but something new. And so what they decided to do was to use the German words enthalten and zusammen. So Z stands for zusammen, at least according to my 32-year-old last semester of German in college course that I took, German 1. I went to a state school. We didn't have to have these foreign language competencies. Although at the time in graduate school, it was required that you had some sort of working knowledge in German because all the organic stuff was in German. And they subsequently got rid of that rule when I got to graduate school. So the E and the Z are probably the things I remember the most about my one semester of German. So zusammen means together. And then E stands for enthalten, and that means across. So they use the German letters and the German words to basically create a cis-trans, an equivalent of cis-trans. And they said, we're going to develop a system that's going to give us, we're going to be able to tell which of these two groups is higher priority, which of the other two groups is higher priority, and then take the two high priority groups and they're either together or crossed. So they came up with these sequence rules. And so these sequence rules are used to determine priorities of molecule or priorities of groups, but it's only used for EZ and later on for RS. It has no reality in terms of these groups are more important. It's just a naming priority. So everything is based on atomic number. So let's see. If we go back here to the book, let's take number A. So let me see if I can remember. I got a bromine, an ethyl, an isopropyl, and a methyl. So a bromine and a methyl, ethyl, an isopropyl, and a methyl. Okay. We're probably going to end up doing all four of those molecules because that'll get us all the examples. Okay, so the first thing we do is we look at the atoms that are attached to the double bond. So we look at this atom compared to this atom. Now remember, intersections are carbons, ends of lines are carbons. So I'm probably going to expand that out to be a CH2CH3. Initially, if I don't quite see that it's a CH2CH3 group. Okay, so what's attached to this carbon-carbon double bond? A C and a Br. Do they have different atomic numbers? Yes. Which one has the highest atomic number? Or higher? Bromine. So that means bromine then is my high priority group. Okay. So now I do the same thing on the other side. I'm going to say, okay, there's a carbon. It has one bond. It needs 3 hydrogens. Here's a carbon. It has 3 bonds. It needs 1 hydrogen. And then I've got my CH3 and my CH3. And hopefully you recognize that top group, that this top group here is called an you're close, isopropyl. It's got 3 total carbons, with the CH3 group with the isopropyl. So that's the isopropyl group. So now we follow the same rules, except that I start out with a tie. Carbon versus carbon, tied. So what do? I now look at those two carbon atoms and I say what atoms are attached to each of those two carbon atoms. So what atoms are attached to the isopropyl CH? 1 H and 2 C's. So I like to write this in brackets. I think they like to do that too. So 2 C's and 1 H. What's attached down here to that carbon? 3 H's. 3 H's. So now I'm going to compare that to those two sets of atoms. And I'm going to do this a little differently because I'm going to make it more general. What I like to do first is I'll look at the collections of the two atoms. If there is a single atom that has a higher atomic number than everything else, it wins. It wins priority for the group.
That CH3, you said it's attached to 3 carbons. Wouldn't it also be attached to 1 carbon? I mean, you said it's attached to 3 hydrogens. Wouldn't it also be attached to 1 carbon?
Exactly. The one carbon it's attached to is the double bond, which is the same carbon that the other one's attached to.
So you don't include that in the carbon?
So we don't include that because what I'm trying to do is tell the difference between these two. So the group, so the carbon, this carbon, I'm ignoring. I'm just looking at the entire group beyond the double bond. Okay. So if I looked at these collections of atoms, I see hydrogens and carbons. Now, in this case, one of the group has carbons, the other group doesn't. So we could look at this a couple ways. This one has the highest priority elements, which are carbon. It gets the high priority. If you don't like that, you could say, okay, this hydrogen, basically, that hydrogen is canceling 1 hydrogens here. So I've got 2 carbons versus 2 hydrogens. Basically, I've got carbon versus hydrogen, carbon wins. So 2 carbons and a hydrogen wins against 3 hydrogens. But it's really the fact that the one has the 2 carbons. That has the highest atomic number of that set. And so that one's the higher priority. So in this case, this molecule has what geometry? E or Z? It's Z. So this is the Z one. Now I want to go back for a minute and talk about that. And now I could get into giving you, I could give you groups. So let's say we're comparing these two groups. Let's say we're comparing a CH with a CH2 with a Cl. And let's say I'm comparing that, and I might as well go, let's say I'm comparing it to a CF3. So if I'm comparing these two groups, imagine they're attached to a double bond. Well, I don't even have to imagine that. I can just say, okay, they're attached to a double bond. I'm trying to determine which one has higher priority. So carbon versus carbon, tie. What's attached to this carbon? 2 H's and a Cl. What's attached to that carbon? 3 F's. Which one wins the priority? Cl does. Because Cl has the highest atomic number. So a single Cl beats F. It's not a question of whether there's 3 F's there. It's just simply a question, Cl beats F. And Cl, well, Cl's with the H, Cl would be H2.
I doubt this is something we're ever gonna encounter in this class, but What if it's two of the same element and they're different isotopes? Would that?
So then the rule is that the higher atomic mass wins. So there are two isotopes that we use in organic. We use the H1 and we use the H2, the hydrogen with mass of 2. The hydrogen with mass of 3 is tritium, that's radioactive. We don't really use that. We use a hydrogen of mass of 2 a lot. That hydrogen of a mass of 2 is called deuterium. Of course, this is just a normal hydrogen. So this deuterium is oftentimes labeled as a D. So it's not out of the question to have a molecule that has a D in it, that has a carbon attached to a D. And then the first time you encounter that, you look at the periodic table and they go, there's no element D on the periodic table. That's because it's the mass, it's the hydrogen with a mass of 2. If you know anything about nuclear reactors, D2O is called heavy water. That's what they put in most of the reactors to absorb the stray stuff that comes off when you're doing nuclear reactions. But we use that in organic a lot. What it basically means is if you had a hydrogen versus a deuterium, hydrogen's the lowest every single time. And we'll talk more about that, but yes, isotopes, same rule, atomic mass. All right, everybody still with me? So what we do is we just basically will continue going down the line until we find a point of difference. Let's go back to there's got to be a good one. Oh, the next one has a really good one. So let's see, isopropyl ethyl methyl aldehyde. Isopropyl ethyl methyl aldehyde. Again, might be worth the extra couple seconds to draw in the groups here. So that it helps you see not only in naming what the groups are, but also in this case what those groups are I'm going to be identifying. So in this case, let's do the two on the left. Which one has the higher priority of the two groups on the left? The top group or the bottom group? I heard top. Do we all agree that it's a top group? Yes? No? Yes? Do we all know why that's the case?
It's got 2 carbons.
So carbon versus carbon tie. That carbon has 2 C's and an H. What does this carbon have? 2 H's and a C. This being the other carbon. So 2 C's and an H versus 2 H's and a C. If you can't start canceling stuff up, you're basically down to C versus H. So isopropyl high priority.
Why are you doing the bottom one instead of the middle one?
Why am I doing the bottom one instead of the middle one? Which one?
Like, for the bottom, like, which one are you measuring?
I'm doing this one.
Oh,
It has to be the atom that's directly attached to the double bond. Now, if we had a system where the top and the bottom one were tied after these 2 carbons, we then go on to the next carbon and compare those two. And whichever one wins the priority. So we can continue on down the line until we find a point of difference. And if we don't find a point of difference, then the groups are the same. And there is no E or Z. Now we go to the next one and we say, okay, carbon versus carbon. What's attached to that carbon? 3 H's. What's attached to this carbon? An O and an H. But I got a problem. My problem is I'm comparing 3 things versus 2. It's not a fair comparison. Right? I'm comparing 3 hydrogens on the CH3 versus only 2 atoms for the bottom one, and that's not fair. I need to compare 3 things versus 3 things. So what happens? That was going to be a rhetorical question, but feel free to answer. So I have to draw this thing called an equivalent structure. So what happened was Cahn-Ingold-Prelog, they said, we can't have this. We can't have 2 versus 3. We can't have 1 versus. We need to have the same numbers compared every time. So they said, well, let's create these things called equivalent structures. Equivalent structures occur whenever you have multiple bonds. So over here, I'm going to write my aldehyde. I need to turn that aldehyde into something like this. And I'll even put that oxygen in there. So what we do is we create a 4 attached carbon with 4 bonds, but I erase the double bond. Now the rule says that I must replace the multiple bond with a multiple number of single bonds. What does that mean? That means that I have to replace the carbon-oxygen double bond with 2 carbon-oxygen single bonds. If it was a carbon-carbon triple bond, I'd be replacing the carbon-carbon triple bond with 3 carbon-carbon single bonds. So the multiple bond is whatever it is. So in this case, what I have to say is I have to say this. Okay, here's my carbon. Here's my double bond. Here's 1 oxygen. There's a second oxygen. So for that carbon-oxygen double bond, I've now replaced it with 2 CO single bonds. Okay, does everybody see that? So the problem is the oxygen. I've got an oxygen to carbon double bond. So I need to replace that with now 2 oxygen carbon single bonds. So this is what we call the equivalent structure. And it's pure fantasy. It doesn't have any reality. It's just used in naming. That's all it's used for. But now I can compare 3 bonds versus those 3 bonds. So now when I say for this aldehyde, what's attached to that carbon, it's 2 O's and an H. Because that's what it is in the equivalent structure. Okay.
The reason why the additional C is added in the equivalent structure is because if there's another tie, you go to what's attached to the oxygens then?
Sort of. The rule says that I have to replace the multiple bond with multiple single bonds. And really what I'm talking about is both ends of the multiple bonds. So another one, let's say I had a carbon-carbon triple bond. My equivalent structure there would have to have both of the carbons having 4 bonds. So for this carbon, I would say I need 3 carbon-carbon single bonds. 1, 2, 3. Because I just replaced the carbon-carbon triple bond with 1, 2, 3 carbon-carbon single bonds. For this carbon, same thing. I have to replace that carbon's triple bond with 1, 2, 3 carbon-carbon single bonds.
And we don't add hydrogens to balance it out.
No. So initially you might look at that and go, so what? Those carbons are just hanging there? The reality is that if you ever had to judge those carbons, they would have 3 hydrogens attached to them.
Oh.
But we don't put them in. We don't put them in. So this is the equivalent structure then of this. And the important thing is, okay, what's that carbon got attached to it? 3 C's. So now I can compare it to whatever else because they all have 3 things attached to them. Right. So that's equivalent structures. But they have nothing to do with reality. I mean, my example with these things is long time ago when not even this building was here, the other science building was over where the parking lot is. Some students came in my office and they're like, Dr. Weaver's talking about phantom carbons. And Dr. Weaver taught here for 45 years. He forgot more chemistry than I will ever know. But I'm like, okay, phantom carbons. Because he would go off on tangents, but that's not a tangent. That's like, okay, what is he talking about? And I'm like, what are you guys talking about? Oh, well, we were doing like easy. And I said, oh, okay. Now I think I know where the phantom carbon talk is coming from. Because that's basically what these guys are. These are phantom carbons. They don't exist. But they're being used in order to figure out the priorities. And so again, Cahn-Ingold-Prelog, the task they had was to come up with a system that would never give ties. And so this is just how they decided to handle multiple bonds. Okay. So again, with this discussion and a little tangent, now we come back to the point at hand, which is which one of those two groups has the higher priority? Top or bottom? Top or bottom? So 3 hydrogens versus 2 O's and a hydrogen, which one wins? 2 O's and a hydrogen. Bottom one has the higher priority. So this one has the 2 high priority groups across from each other, so that makes this the E isomer. So what you have to remember is that when we have these groups with 3 or more non-hydrogen, we need to use the E or Z terminology to tell us what geometry we have. And so you have to remember whether E is cis or trans or whether Z or cis or trans. What did I not write? I didn't write down the great analogy or the great, mnemonic that we use. And the mnemonic that we use is Z, Zame, Zide. So Z, Zame, Zide, that's cis. And you only have to remember one of the two. So you just have to remember the E is the trans version. All right, so that's how I didn't see that in the book, but it's in another book from years ago, right? So that's how we do E and Z. So let me do one last group comparison. So what do I want to do? So let's say I'm comparing those two groups. And later on, we're going to actually have 4 groups that we're going to need to determine 4, 3, 2, 1 priorities. So we're just doing 2 at a time here. But let's say I've got these 2. Take a minute. And which one has the higher priority? The top one or the bottom one? So where's my... Here's my 2-minute egg timer. So which one has the higher priority? No, don't answer yet. You got 2 minutes, and then I'll ask everybody. This is one where if I was farther prepared, we would use the system, the classroom system, but we don't need to use that today. So, for the first 2, top or bottom, which one's the higher priority? For the second 2, which one has the higher priority, top or bottom? Okay, time's up. So for the left 2, how many people say the top one has priority? How many people say the bottom one has the priority? Oh, we're kind of split 50-50. Okay, now for the right 2, how many people say the top one has the higher priority? Bottom one has the higher priority. Okay, so majority answers that. Now for the one on the right, this is a problem that is written to ensnare you. That was another good Dr. Weaver quote. Well, that problem's set to ensnare you in it. Let's go back to basics. Carbon, carbon, tie. What's attached to this carbon? 2 H's and a C. What's attached to this carbon? 2 C's and an H. Tie? No. Which one wins? The bottom one. So why did you choose the top one? Because you saw the iodine there and it sucked you in. Oh, well, iodine has the highest priority of everybody. So that's going to be the highest priority group. Not if you don't get there. So if you don't get there as you're going down the line, it doesn't win. So you have to be careful with that. Because sometimes I'll put a bromine or an iodine or a chlorine in there just to see how far down the line you go. So you got to take it step by step. Okay. So this one is the higher priority. So that's kind of the Cahn-Ingold-Prelog rules in a nutshell. And we're using those to basically do one side, which one has high or low, other side, which one has high or low. Are they on the same side or are they on opposite sides? They get the E or Z terminology. Now, you can use E or Z instead of cis or trans. You can always use E or Z, but you can't use cis or trans all the time. Only for very specific double bonds. What other questions do you have?
Question, the 2.37. It says, like, the answer explanation says the alkyne should be numbered so they either get the lowest possible position number. When there's a tie, it goes to the alkene, but that's not the case in this question.
Okay, so question number, how do we name this? So how do we name that molecule? So the first thing you need to remember, and this is going to get more complicated for Monday, because now they're starting to throw in every functional group and multiples of the functional group. Now, fortunately, the first thing you'll see two charts for Monday's reading. There's one chart where I added a statement above it that said, you do not have to memorize this chart. You'll get it on a test or a quiz. You just need to know how to use it. So what we need to know for this molecule is which of these two functional groups has a higher priority than the other. And according to that chart, it's an ene-ine, which doesn't make any sense, honestly. They should have used the Cahn-Ingold-Prelog rules to determine which groups go at the top, but they didn't. So that's why we need to use the chart. Because I don't have the chart memorized. I'm not going to expect you to memorize the chart, Bobby.
So what kind of a hydrocarbon is that?
It's a hydrocarbon for certain. It's just an alkene and alkyne together.
So can you have all three in one? Or?
Oh, you could have multiple double bonds. You could have multiple triple bonds. Basically, this one does have single bonds and double bond and triple bond. It has all of them. But the question is, so who gets priority here? And I hate this example because if it's an ene-ine, we're going to learn that the name that comes last has the priority. But not in this case. It's an ine-ene, it's an ene-ine instead of an ine-ene. So it's an ene-ine. So that's the way the name works. But yet the double bond gets the priority. So we got to choose the longest carbon chain with both the double and the triple bond in it. So that's going to be let me try and remember how to draw this. So it goes like this, right? With that, then that with a triple bond. Where's the triple bond go? Here?
Right.
Then a methyl? Okay. So then we've got a number. So here's our longest chain, correct? Our longest continuous carbon chain that contains the double and triple bond. Now we got to number it. So how am I going to number it? And we have to number from the end closest to the higher priority group. So in the book they said you could number to give either one of them the low number. When you give the double bond the low number. Correct. So we have to number this to give the double bond the lowest number. And so then it has to go 1, 2, 3, 4, 5, 6, 7, and 8.
Wait, why are we giving the double bond the lowest number?
Because it's the higher priority. Because this is an ene. So they tell you in this long chart that the double bond has a higher priority than the triple bond. So when you look at that chart, and I'll bring printed copies of it on Monday, the double bond always has the higher priority over a triple bond.
But I thought that was in like the particular example in the book, because either way it'd be 2 for one of the bonds. It could be, the low pick would be 2. But like in this example, the triple bond would have 2. And then the double bond would have 3.
Yeah, you can't have the triple bond being 2 and the double bond being 3. The double bond's got to have the lower number. So we haven't gotten to substituent yet, because this is different numbering than alkane, because you've got a number closest to the double bond. I don't care about the substituents. You've got a number from the end closest to the double bond.
In the reading here, it says that the longest continuous chain is made of, it's just talking about this example, 7 carbon atoms, and the chain is numbered in the direction that gives the first multiple bond the lowest location. So in this example...
Yeah, would it have to go the other way? See, I don't think so. I think it has to go to give the double bond the lowest number. I know I'm contradicting the book.
But the answer for that question is...
It's not this one?
It gives the other numbering way.
All right, then I guess I'm wrong. Which doesn't make sense. All right. Okay. There shouldn't be an either or here. So that's the longest chain, numbered correctly, I guess. Okay, so then in terms of the final naming here, I got a methyl group of carbon 6. That's easy enough. I got a 6 methyl. 6 methyl what? I got 8 carbons, so it's a 6 methyl oct. Oct what? It's still an ene. So that means it's a 6 methyl oct ene. But I got to tell the number of where the double and the triple bonds are. So.
Can you explain why it's an ene instead of an ine?
Because that's what they told us. Because they decided that a double bond was higher priority than a triple bond. And that they were going to name this with the ene first and the ine second.
So it's never an ine?
No, it's never an ine. Because they decided that was never going to happen. I mean, this is why they didn't invite me to the committee, because I would have said, let's use the Cahn-Ingold-Prelog rules and give the triple bond priority over the double bond. But they ignored that for some reason.
So if they say you should give the double bond priority, why is it numbered that way?
Well, that's my question, but they're not answering questions now. They've already decided these are the rules. So you number from the end closest to, if it's a double and a triple bond, you number from the end closest to either the double bond or the triple bond, whichever one comes first.
Okay.
But then if it's tied, you give priority.
Then if it's tied, then you give the priority to the double bond, right? So only if it's tied, see, I don't understand this. But these are the rules. So, final thing. This is an oct ene. I need to tell you where the double bond is. So what's the first number in the double bond? It's 5. So this is an oct 5-ene. Where's the triple bond at? 2. So this is a 6-methyl oct 5-ene 2-ine. Okay. So it's only going to get worse on Monday because we're going to have a whole bunch of other groups. But with the other groups, the table of priorities actually makes sense. I think this is the one exception when you have a double and a triple bond where it doesn't. But for the other ones, the things that are at the top of the list are going to be the things that we need to give the low number, and they're the names that are going to come at the end of the name. So at the top of the list is carboxylic acid. A carboxylic acid gets number 1 priority, gets the number 1 number. And then it comes last, so it's an oic acid. So as you go through, there's a lot of different possibilities. So as we go through, we'll spend some time on Monday. You may come in and just go, but if you have specific questions, take some more cards. If you have a question from the day, or send me an email. I have one question. Somebody wanted me to go over this to put in the discussion group, which I will do. I don't know if anybody looked at the discussion group, but I answered all the questions that I was given on Wednesday. They're all anywhere from probably 8 to, I think the longest one's maybe 14 or 15 minutes. So they're going to be shorter videos that I'll answer the question. So this is where if you have a question, shoot me an email, bring the 3x5 card to class, and we'll continue on with this on Monday.
Can you go back to the first page?
Can I ask you a quick question? So
Yeah.
on that one, how would you then tell if it was Z or E?
Okay.
Do you want me to put that on the card or something? Or?
Yeah, take a picture of it. Let me see. Oh, that's not going to be a good picture. And the thing is, I'm going to put the video online, so all these slides will be up there.
Okay.
Okay, how do you determine if it's E or Z?
Yeah.
It has to be E or Z because, so what I'm going to do is I'm going to say there's a hydrogen right there.
Okay.
So now I'm going to compare ethyl to methyl.
And we're looking at the double bond instead
We're
of the
looking at the
triple
double bond. A triple bond is linear.
Okay, all right, okay.
So ethyl versus methyl.
Doors, so I'm gonna be hearing it either way.
So ethyl wins.
I don't think I
Got it, okay.
Over here, hydrogen versus that,
have a whole bunch
everything wins against hydrogen.
like I'm
Right.
really caught up with it.
So, okay, because that's
So in
carbon.
front of this
I don't like understand all of it.
should be
Got
E.
it, okay. I was just confused as to whether, what multiple bond you were looking at, but that makes a
Yeah,
lot of
but
sense.
triple bond doesn't have a stereochemistry.
Right.
Only the double bond.
All right, thank you.
Okay. You too.